I finished writing the article about category theory. Uh, it's kind of a interesting journey for me because I'm still an undergraduate and this was done through solely self-study. So I had to look exactly uh, what category theory is and what's the purpose of it, and also uh, how it what is the origin of category theory. So this is my article. It's kind of a lengthy one, so I tried at some diagrams as well. This was done by me through LaTeX. uh, so yeah, let me walk through this article. So first paragraph just sums up um about mathematics. So, as mathematics, I guess learning about mathematics and applying mathematics are two different things because uh, this I started with a quote of a prominent mathematician David Hilbert, which says mathematics knows no races or geographical boundaries. For mathematics, the cultural world is one country. So it's kind of goes with the picture I added here. It's kind of a map. It's so I captioned it as the bird's eye view of mathematics. So here you can see every bit of mathematics in this single picture. Here you have the ocean of logics and the planes of analysis, topology, algebra, geometry, and basic logic also here, and arithmetics, hills of number theory. It's kind of a wonderful to look back. uh, However, uh, these articles based on this article does not teach you what category theory is, rather a brief overview of uh, the subject. So first paragraph is just an introduction what category theory is, and not exactly what category theory is. It's kind of an introduction to pure mathematics. So learning about mathematics and applying mathematics are two different things, is the main idea of this paragraph. So to get some insight into this question, we need to look at the underlying structure of mathematics. So underlying structure of mathematics is kind of a complicated and very messy one for centuries, but okay, it can wait. There is a separate paragraph dedicated to this question, so I will uh, tell you more about that when we get to that later. Okay, so the second paragraph, kind of I use my own analogy for describing mathematics. So I use a large factory with several separate floors, each equipped with different tools, sometimes unique machines for various purposes. So I here compare the whole subject, whole mathematics to the large factory with several separate floors. So here, I came. This metaphor is I came my own. This metaphor is my own metaphor, or rather, the analogy for the mathematics. So here, what I mean by this is, imagine you have a question in uh, algebra, or let's say you have a question in analysis. You have to prove some claim. So according to this analogy, you have to um, input that particular question into the analysis flow, because this factory consists with several separate flows. Okay, so several separate flows, and one of the flows is called analysis flow. So if you have a question in analysis, you have to input it to that flow. Then this flow has to be equipped with different tools, sometimes unique machines. Those are the different things in analysis you have. I mean, various proof techniques and various theorems in analysis. Those are the tools and machineries in the uh, analysis for. So you take the claim and you have to have an idea what you are going to do, then you use a kind of a proof techniques and uh, proof techniques and the machineries analysis consist with, then you have to solve that particular question. So kind of a interesting analogy that I came up to describe mathematics. Same goes for algebra. If you have a question in algebra, you have to input that to the algebra flow, and you have to use the machines and tools in algebra to solve that uh, particular question. So it's a kind of interesting analogy I came up with. But if you go further, sometimes uh, complicated mathematics problems. Uh, Imagine you have a question in topology, but sometimes it is more convenient to use tools in algebra to solve it. Due to this, we have to have connection between these flows. So it is true that the question arise in the topology, but you need tools in algebra to solve that. So because of this, the new branches of mathematics are born. We call such uh, subjects like, for examples, algebraic topology, analytic number theory, and differential geometry are those kind of subjects which are made of two or more branches of primary mathematics. It's kind of an intersection of the whole field. Okay. Uh, this paragraph solely goes with the metaphor, and uh, although this fact although we are learning mathematics itself means studying the structure of this mentioned factory. uh, so applied mathematics is you have a problem, then you direct it to a separate flow, then you use machinery and tools to uh, examine the question and solve it. It goes with the applied mathematics part, but learning mathematics is studying the core of this subject. So studying the core of subject means in the above mentioned analogy, it goes with the studying the structure of this factory, understand its foundation, and carefully examine each flow structure. By doing so, mathematician can ensure the foundation is solid and each flow has a well-designed structure. So that's the goal of studying the structure of mathematics. To do this, we use logic, sometimes philosophy, as the languages of studying the structure of mathematics. So it was around late 19th century mathematicians began to seek the absolute truth behind the mathematics. This all significantly started with the Georg Cantor's discovery of set theory. It's kind of controversial back in time because the colossal debates were broke up, and mathematicians fractured into two groups, one intuitionalists and other group is formalist, like David Hilbert and so on. Henry Poincaré is a intuitionalist, and he criticized this idea of Cantus because he came up very controversial ideas. I mean, some saw it as a very elegant way to describe the mathematics, the language of mathematics as a set theory, but some saw it was a disaster, like Poincaré. Uh, uh, okay, for example, continuum hypothesis. So Cantor uh, came up with this idea that you cannot have uh, an infinity bigger than the set of natural number sets and smaller than the set of real numbers. So there is no infinity in between those two infinities. It's kind of a comparing this infinity concept, and it's very advanced to the day we do not have a proof for continuum hypothesis. So due to these controversial ideas and uh, uh, this inspired mathematicians to seek into the absolute truth behind the mathematics. So then there is this Hilbert's program. As I remember, there were about 27 problems Hilbert proposed to solve in order to uh, prove the consistency of mathematics. So first problem is a continuum hypothesis, as I remember. So by the way, this is all about the history of mathematics, and the category theory first uh, pop up in 1945, a paper by Ellenberg and MacLean entitled as General Theory of Natural Equivalences. So took this abstraction to a whole new level, giving birth to the category theory. So this is Georg Cantor. So this is about the abstraction of category theory. Uh, okay. Uh, Here the Ellenberg and MacLean. So in this paragraph, I briefly explain what category theory is. So I'm sure you are familiar with the concept of mathematical objects such as sets, fields, groups, rings, and so on. So category is also a mathematical object. So it consists of four components: objects, morphisms, compositions, and identities. So these components are subject to the identity law and associativity law. So see, objects are mostly mathematical objects such as sets, groups, rings, fields, and so on. Morphisms are relations between those objects, and composition is just composing morphisms, and identity is just the it has the same meaning as the natural identity. I mean, if you compose a morphism with the identity morphism, it does nothing to the original morphism. It equivalent to say that 1 multiplied by any number gives the number back. So that's all about this uh, category. So to be a category, we have to have four components: objects, morphisms, compositions, and identities, subject to uh, associativity law and identity law. Okay, this is a commutative diagram. This is a way of describing, I mean, this is kind of a way of presenting the category theory in action. So category, now that this is this paragraph dedicated to some examples for category theory. So set is a category under so the category of sets. Our objects are sets, morphisms are just set functions, and it is subject to composition and associativity law. So and also groups also form a category because group is just a set with an added structure. So or otherwise group is just a set with a binary operation, a single binary operation. So it also forms a category. So in this paragraph, go on saying that how the categories are represent. Basically, the categories are represent using the commutative diagram. In order to this diagram to be commutative, uh, this this path should equivalent to this path. I mean, if you compose f and g, it should give. If you first go a to b by f, then b to c by g, if you compose them, then these two roots should be equivalent. If so, you can say this diagram is commutative. So in category theory, commutative diagrams play a vital role in the core of the subject. So uh, this paragraph is dedicated to this one. In this in this paragraph, I introduce the concept of functors. So functors is a mapping between categories. uh, there are two main functors. It you can look it as just a function between two sets. So a functor is also a mapping between categories, but it's more powerful than a function. So uh, in order to be a functor, uh, let A and B two categories and F be a functor between them. Let's examine the mechanism of a functor and what it does. The functor takes object from the functor acts between two categories. So it takes objects from category A to objects from category B. So it takes morphism from category A to morphism from category D. So uh, and the composition is regular, not regular composition, because this binary of this composition should preserve. This is kind of like, if you're familiar with group homomorphism, this is kind of very similar to group homomorphism, and it has uh, a correlation between functors and group homomorphism. So in order to be a functor, composition should preserve. So for example, for functors, we have forgetful functor. Forgetful functor, by all means, uh, forgetful functor comes with forgetting the facts. It means if you want to uh, convert group into a category of groups into a category of sets, so you use the forgetful functor. It forgets that added structure to groups and it gives original set. Then you have the free group functor, which you can manipulate sets into groups. So there are so many functors between categories. So this is a very complicated commutative diagram you usually come with uh, when studying the category theory. So in the last paragraph, I just summarize what is the article about. So category theory is very advanced subject, but it still lacks uh, of some of the details, so that we can't consider it as a grand unified theorem of mathematics. So this is what my article about the category theory.